Okay, so today what I'm going to be talking about is a research agenda that my group has been pursuing for the last 3 years since I started at UCLA. And that is really thinking about how can we think about the generality between different problems in sustainability and come up with frameworks which help us learn from one problem and apply it to another. So specifically, the space I'm going to be looking at as the backbone of a lot of this research is atmospheric sciences. So if you think about atmospheric sciences, it's one that has dominated the news headlines all through last year and continues to do it this year. So if you think about any part of the globe, there has been some extreme weather event which was totally unexpected. Just earlier this year at UCLA, we had record rainfall, which has never ever been recorded in all of its history, to the point that there were being comparisons being made between UCLA and Seattle, which is not something anyone in Southern California really enjoys. So this is the status at which we are right now, where we are really thinking about what weather patterns will influence almost every aspect of our daily life. So on the other hand, the other dominating part of the news was AI for the last year and continues to do this year again. There has definitely been a lot of momentum in from the general media as well as everyday citizens about how AI will influence a lot of things in our daily life. We've seen this for language, but it's no longer just about large language models. We are seeing this span into domains, whether it relates to vision and decision making, and also science, right? So, amongst all these big news, I guess one of the biggest advancements that AI has enabled has been through AlphaFold. And this is also very inspirational for the community to think about how we can then solve other grand challenges in this space. And the challenge for me and my group, as well as the broader community that I want to highlight today, is how can AI really bring about fundamental change in atmospheric sciences? So this is generally how my lab works. So it's a lot of inspiration has happened from my training at Stanford, and in turn, that has also been propagated through Cornell. I feel a lot of research happens when you can go deep within AI as well as within a different domain and then think about intersections. So a lot of my research focuses on the intersection of genital models and decision making. And I try to ground it actively by thinking about how we can do modeling over space and time for long time horizons. And this intersection is what I'm really excited to talk about today, which is how do we build new foundation models for atmospheric sciences. Now, when I think of this term atmospheric foundation models, the key question that comes to mind is what exactly is a model? And this is also a place where we'll find a big separation in the world of an atmospheric scientist versus an AI scientist. Now, in AI, especially in machine learning, we're used to thinking of models as either in the traditional world as taking some data, learning some predictive model over that data, and then using it to solve a specific task. And we can do this over and over again for different kinds of domains and different kinds of tasks. What's become a bit new in the field is to think of it not as a purely supervised paradigm, but one that brings in unsupervised learning to its core. So now we first learn a big foundation model over large-scale data sets from the internet. And then we think about how we can adapt these models to solve specific tasks of interest. This is exactly the paradigm that's enabled the advances we were looking at for language, vision, and some of our own group's work in decision making. But when you go to a domain scientist, especially in atmospheric sciences, they think of a model as very different. They think of a model as a system of differential equations which governs the flow of matter and energy into the atmosphere. And these physical models are an amazing advancement for humanity This is what was acknowledged in the 2021 Nobel Prize in Physics, and has resulted in a very reliable technology over the years. So this plot on the right is showing how the skill of these physical models has been increasing over the past few decades. So now we can, both for the Northern Hemisphere and the Southern Hemisphere, we can have very high forecasting skill up to 5 to 7 days. And just thinking about the impact in each of our lives, whether it's like planning a trip, and then thinking about how it affects other things indirectly, like it affects agriculture in a big way, which governs how we can ensure food security. The importance of this technology cannot be underestimated. So this technology, however, faces certain challenges, which is reflected in how there are still periods of time from 7 to 10 days where the progress has been quite slow. And this is what needs to be accelerated if we have to confront the extreme weather conditions that we face today. So if you think from a more formal perspective, we can think about three different limitations with physical models. First is they rely on physics, which at very fine resolutions becomes incomplete. And that is hard. That is a hard thing to learn directly from first principles. The second is physical models actually also rely on supercomputer scale. So there are only a few national laboratories around the world which have the access to train these or specify or run these models in simulations, combine them with real data, and that prohibits widespread critique of how we can improve these models and democratize this process. And the third thing is that because of the resource constraints and the heaviness of this technology, it's not easy to repurpose it very easily for other domains in sustainability, which depend on weather and climate, even though they may not be directly using atmospheric data when we try to build systems for those kinds of domains. So think about agriculture, think about insurance, think about finance, and a lot of other places that depend on weather and climate, but we don't really have a direct access, direct from raw data to making predictions to enable these technologies. On the other hand, foundation models are really good at addressing some of these limitations. So for foundation models, the performance scales not only with compute, which is also true for physical models, but it also scales very well with data. And as we all know, data availability has been increasing at unprecedented rates, a lot of thanks to the increase in satellite technology, which enables this scaling. And the training of foundation models could be expensive, as we all know, with very few labs having the resources to do it at very large scales. But this is a one-time cost. Once this has been trained, you can adapt this model very cheaply and use it for many different tasks. And finally, foundation models, one of the most exciting things about them is that they learn representations, which can then be applied very broadly to different domains, even outside of weather and climate. And that's going to be something I'll also touch upon towards the end of my talk. So what is today's talk about? Well, it's going to think about what are algorithmic primitives for learning atmospheric foundation models. And we will essentially walk through the entire machine learning pipeline and question every step of it. So we'll think about the data sources, we'll think about the model design, and we'll think about the adaptation strategy, which will enable us to learn general purpose models for atmospheric sciences. And when I say general purpose, I'm really thinking about adapting these models across a wealth of tasks. So some I'll demonstrate in our current work, and then I'll show also what other researchers have been using to build on our work. So I'll show results in weather forecasting at different time ranges. We'll look at downscaling at different resolutions. And we'll also think about how we can go from weather to climate when it comes to thinking about making predictions over decades. So let me begin this talk then and start enlisting the three main parts of today's talk. The first one is going to be thinking about what exactly is the pre-training objective. And this has been a fundamental insight for language as next token prediction, for vision in terms of masking. What does it mean for atmospheric data? What is that fundamental pre-training objective? The second part of the talk will then think about how we can scale these systems by thinking about clever ways to do data fusion and designing the architecture which respects the domain constraints imposed by atmospheric domains. And finally, we'll think about how these models can be flexibly adapted to different kinds of use cases. So beginning with the first part of the talk, where we think about objectives, uh, I'll start with the very basic objective, which is weather forecasting, and we'll see how we can make weather forecasting a bit more general to enable the training of a machine learning-based foundation model. So in its simplest form, weather forecasting is simply saying that if I had the state of weather at time t, how would this weather look like at time t plus h? Now, this simple question actually does not have a single answer. Depending on what the lead time h is, we have actually very different systems in place that are used today. So if you care about really small h in the order of minutes to hours, you could actually not beat the simplest baseline, which is persistence, which is to just imagine that the atmosphere does not change in h and just give the answer as xt itself. If you go to very long time scales in the order of weeks to months, then you have another simple baseline called climatology, which is simply the historical averaging of the weather. And that's something which is really hard to beat. But in between is where the magic happens, and that's where numerical weather prediction models have demonstrated enormous success by really expanding on persistence and climatology and giving us accuracies which enable their use in different domains. So given this history of how weather forecasting happens today, we will be asking whether we can think of a foundation model based on AI, which can extend this frontier of predictability. So it should be improving upon numerical weather prediction. And then as we go to longer time scales, it should not be doing worse than climatology. So with this kind of goal in mind, let's think of how you would train a machine learning model. Now, the simplest solution could be just train a direct model, which goes from xt to xt plus h. So this is known as the direct forecasting objective. But this objective, even though it's simple in how you instantiate it, this objective actually is not very efficient in terms of how we are going to be training a different model for different age. So this dependence on a single age is something which we have to, which is not really good for direct, because we actually, for weather forecasting, we care about a range of different age, all the way from a few hours to going up to many weeks or months in advance. It's also not good because it doesn't use any of the intermediate supervision. So if you look at historical data, we actually have a very fine-grained in time recordings of the weather at different time steps in between. But a direct approach does not use that directly. So in that sense, it's not using the supervision that we have in a very efficient manner. Alternatively, we can do an iterative approach. So here the idea would be to break down our lead time h into smaller steps at the step size of delta, and then try to predict only delta time step ahead. So if we do this iterative way of forecasting, we have to run the model many, many times until we reach our desired lead time h. So this is actually very similar to how autoregressive models work. So you predict one token ahead, and then you keep doing it multiple times until you have, let's say, finished your paragraph and so on forth. This is also how physical models work. So physical models, when we use them, they don't directly predict at your desired lead time. They will also actually simulate essentially the weather at all the intermediate time steps until they reach the target lead time. But with these models, the downside is that you can actually have compounding errors. And this happens if your delta is really small. So this dependence on delta, if it's really small, the task is easy, but compounding is large. If it's too big, in the limit, it will just look like a direct approach. So this is a downside of the iterative approach. So we compared all of these approaches in much detail, and we also have a package which allows you to then do very fair benchmarking that I would encourage you to look at. But then what we have proposed in recent work, just from a couple of months back, is this whole process of doing actually what we call as a randomized joint iterative approach. So this approach, let me define what it does in 2 simple steps. So the first keyword here is randomization. So one thing we noticed is that the delta, keeping it fixed, allows you to learn only a subset of features which may or may not be applicable at different ages. So essentially thinking about the features that you need for predicting how temperature changes between day and night would be very different from predicting how temperature changes from now to 1 week ahead. So the first thing we do is, instead of choosing a fixed delta, we randomize the delta and we look at 3 small intervals, 6, 12, and 24. So for different iterations of training, we have different deltas. And then finally, we think of the compounding error problem, which happens essentially because we are only predicting one time step ahead during training, but at testing, we are using multiple simulations. So at test time, what we instead do is we predict multiple time steps ahead. So we define this value k, which denotes how many time steps ahead we are doing. So if k was equal to 2, we would predict delta 1 and 2 times delta 1, and same for the delta 2 and delta 3 time steps ahead. So with this kind of randomized joint iterative forecasting, we actually get a multitask objective for pre-training our foundation model. And this multitask objective is derived from understanding the nuances of the atmospheric domain, where delta, when it's very small, it learns day-night features. And when delta is big, it learns features which are useful for then making very long horizon predictions and seeing how over the course of many days, the important features that the model should learn in order to do good forecasting. And doing k delta time steps ahead, not just delta time steps ahead, reduces the train and test mismatch and mitigates compounding errors. So we ablated these design choices, and here are some results. So our model is called Stormer here. And if you see Stormer, and here on the left, we are looking at the effect of randomization. So if we have a fixed delta ahead, the RMSC, the lower the better for the 2-meter temperature, is substantially high, but randomizing this value leads to a significant drop in the RMSC across different lead times ahead. Now, the other ablation we did was on the joint aspect of our forecasting objective. And here again, we find that if you predict multiple time steps ahead, there is a reduction in the loss. So now building on this primitive of our objective, we then looked at what happens at scale when we try to benchmark it on the weather forecasting benchmarks. So we looked at WeatherBench 2, released by Google, and we compare against 2 of the state-of-the-art baselines. One was in Nature last year, the other was in Science. And here are how the results effectively look. I think there's some rendering issue, but I'll specify the colors. So the blue is Pangu weather, and the green is essentially Stormer. So Pangu weather is in blue, GraphCast is in orange, and the purple one is persistence, and the black one here is climatology. So early on, if you look at, the persistence one is in black, and the purple one is climatology. So as we see for different variables, as we increase the lead time, we find that the errors, of course, have to increase for all methods because it becomes harder and harder to predict. But compared to the state-of-the-art baselines, Pangu weather in blue and GraphCast in orange, the error increase for us is much, much lower. So at the limit of reaching 14 days, we approach what would be known as the climatology limit, right? So we are actually able to extend the frontier of AI predictability compared to existing methods, which after a certain lead time become worse than climatology, whereas we saturate down to what would be the climatological predictions.
Sorry, can I ask a question?
Yes.
I'm very confused because you just told us that flat line was the persistence, and now you're telling us you're reaching the climatology line. Which one is it?
Yeah, actually, sorry, I think there's some rendering issue, but I might have misspoken. The flat line is the climatology. So I don't know if it's also happening on your side on Zoom, but it's happening when I'm sharing the screen. But this flat line should actually be the climatology.
Can I ask another question? What about standard models? Standard weather models?
Yes, that's a great question. So the red one is the legend actually says IFS. So IFS is the one that is the numerical weather prediction model. So it's a deterministic numerical weather prediction model. And there have been results like GraphCast showed that it can beat IFS last year. Already it's been actually shown that compared to standard models, these machine learning based models are doing better.
And could I also ask, what is the mean squared error in? What are the units? What is the...
Yes, so the units are in the title. So for temperature, 2 meters in Kelvin, this is U is the wind at 10 meters in meters per second, and Q is the humidity. So, and in the paper, we actually have results for a bunch of other variables as well. And any other questions? Okay, all right. So now moving on to the second part. So now we have actually learned a general purpose objective, which allows us to do global modeling of the weather across different time scales. Now, the second part I want to touch upon is how do we scale these systems? Now, why should we even care about scaling? Well, if there is one lesson that we can learn from language is that scaling of data sets really helps improve performance. So we have seen these power laws, relationships between the test loss and the data set size for language models. More recently, actually, again, this is work from Cornell Tech, which has shown that there can be actually limits to the scaling if there is not enough high quality data. So here, if we look at the training, the test loss as a function of the redundancy in the data. So if we repeat the same data multiple times, and that's what's being shown by these points, then the reduction in loss in the bold curve is much lesser than if we had unique data, which is what is shown in the dotted curves. That's something to say about data quality. So it's not just that we can keep increasing the data set. We also need to think about how we can get new kinds of data, which is different from the ones we have seen before, to improve these performance here. So now going beyond language, thinking of this question for the atmospheric sciences, we are actually in a predicament because atmospheric data sets look very different. Firstly, these data sets are less diverse. Often, computer scientists like to think of this atmospheric data set as actually a subset of videos, right? You can think of this as a movie playing where the pixels are denoting some kind of weather variable like temperature over time. But now just think about how much redundancy is there in this kind of data compared to all the possible videos that you have on the internet. This is really a small data set. The other challenge is, unlike computer vision, where videos you might have only 3 channels, red, green, blue, and maybe a time channel that you might care about, in this case, you actually care about lots and lots of different variables and jointly modeling them. So typically in atmospheric sciences, you can easily have in our experiments up to 69 different variables, which are the core values of these variables for pressure, temperature, humidity, so on and forth at different levels. right? So it's really a very multimodal problem that we also need to account for when we are thinking about designing, thinking of data sets and thinking about architectures. So what I'll touch on next is how can we improve the data sourcing for atmospheric foundation models, and then how can we design embedding techniques that can address the multimodal challenge. So the first one challenge is about improving data set diversity. So if you look at what data set are used typically for training atmospheric foundation models, these are all based on ERF5. Now, ERF5 is a data set that's maintained by the European Center for Medium Range Weather Forecasting, and it contains hourly data from 1979 to the present. So this is about 45 years of data at different hours. But this is actually a really tiny data set. So if you look at ERF5, 45 years for 20 every hour, and it has about 225 other variables, that's still 90 million frames. Compared with YouTube, which is 13 billion videos, this is a tiny data set. So when we really use the word foundation model, we should really be aware of like this big difference that we have in training atmospheric foundation models versus what's happening in the vision and language community. There's other limitations also, which an atmospheric scientist will point out with this data set, which is this data set does not capture the other kinds of analysis and simulations which have been done by this domain. So for example, we have this whole field of paleoclimatology, which can go much before 1979, up to even the 1800s, and try to create what weather patterns would have existed in then, even when the sensory technology was poor. So we are ignoring all of that data in ERF5. It also ignores data that we have projected for the future. So a lot of climate model groups around the world create simulations under different scenarios for what future weather and climate patterns would look like, which is completely ignored in this ERF5 dataset. So one of the first things we did to go beyond ERF5 in one of our other models, Climate X, that I'm going to talk about, was to really think about how do we expand from ERF5, and that's where we brought in a new set of data sets from the simulation community. So CWEB6 is one such data source, which essentially maintains an ensemble of climate model simulations all the way from 1850 to 2100. Now, this contains lots of different models with many different couplings and forcings to imagine how future climate would look like. So typically, when you look at graphs of climate change, you essentially look at a range of different futures that could happen. And that's essentially because there are different climate models making different simulations of what would happen as we go into the future. So all of this data is really rich. It's derived from physics and different kinds of physics of what has happened in the past and what might happen in the future. So our observation with this work of Climax was to think about how we can combine ERF5 and CMIP6 to essentially lead to a new foundation model for atmospheric domains. Even though in principle this proposal looks fine, there is a big question here that because this data set is simulated, the utility of this data set over something which is observed will depend on how good the simulations are. So the big question for us is whether the signal to noise ratio actually improves or deteriorates by adding these data sets. So to first study this phenomena, we had to then think about more generally, if we look at our current architectures are all based on variants of transformers. We wanted to see how much does training on some simulation help in the real world. So in one of our other works, which was thinking about this question more generally, we had this study where we designed a transformer which was trained using in-context learning on a certain set of functions. So we looked at functions which were derived from the RBF kernel. And then we looked at their performance when evaluated on kernels which were from a different domain. So we simulated the setup and we looked at how the performance of transformers varies on Mattern, linear, cosine, periodic kernels. And what we found is that even though we are pre-training on just the RBF kernels, the performance here, higher is better, was improving on even other function families. So this was a very promising result for us because that then allowed us to think about transformers as effective ways to generalize over nonlinear function families as well. So this result has much broader implications that I could go over in offline. But in the context of atmospheric foundation model, this was the basis for us to then try it out for doing these weather forecasting, where now on the x-axis, we are looking at pre-training on a simulated data set. So recall the simulated data set was CMIP, and at different points, we are adding more and more simulation data set. And we're looking at how does the performance on the y-axis change on the real weather test set, right? So here, these are different variables. This is geopotential, temperature, wind, and we have more in the paper. We see that in all these cases, increasing the amount of simulation data is also improving real-world performance as measured by this mean squared error. And this holds for a range of different model sizes. So if we increase the model dimension, the gains are higher. So this is very good news for scaling of foundation models. So you can increase the model dimension, you can increase the number of simulation data set, and your loss on the real world data set is decreasing.
I have a question.
Yes.
In that simulation data you showed us, it went up to 2100, and there were a number of different simulations, which I assumed on the vertical scale were making different assumptions about the amount of CO2 in the atmosphere. And I'm wondering, in these simulations that you're comparing with real test data, are you just ignoring everything after the current date, or are you using some of those future projections as well?
That's a great question, and we are doing the former. So we are ignoring everything after the future, only so that we are not biased into like looking at the simulation which is accurate, right? So we are ignoring that, but in principle, if you ignore the benchmarking and doing it in a fair manner, but you just want to utilize these for the best forecast, you could actually even use those future simulations.
Thank you.
They also ask, the ensemble of models that you're using for the CMIP6, are those models that are constrained by previous data, or are they wild ones? So you can assimilate, or it's common to assimilate weather data into these models and benchmark them. And so then you're tuning the set of models that you're using based on the ones that make good predictions. Are you using those or wild ones that make whatever predictions?
I didn't get what's the last thing? Wide ones?
I guess the question is, are you using models that make correct predictions based on weather data, or models that make wrong predictions also?
Actually, we didn't filter based on whether the predictions were correct or wrong. We filtered, so essentially these CMIP data sets that we picked, we just looked at which of these CMIP data sets had variables that overlapped with the ones in WeatherBench. So in fact, the reason of not filtering was actually because we want diversity.
Yeah.
So it's okay if the physics is a little bit different from the one that happened in the past, but the future could be different. So including that in the pre-training could actually be helpful, was our hypothesis.
Can I ask a quick clarification? So did you look into these temporal and spatial resolutions, or let's say you mentioned agriculture application at the beginning, but let's say if I'm a farmer, I want to use this model to make a decision of a specific farm. Would that be feasible, or do I have to downscale, upscale some part of the process? Sorry. Did you hear me at all? Hello?
Yes.
Oh, thank you. Maybe a very simple question is more about a spatial resolution that you are looking for in this foundational model. It's amazing to have this model, by the way. But I'm curious, what spatial resolution are you dealing with? Because temporal resolution is based on the charts you're showing.
Yes. So that's actually a frontier for, I think, research in this space. So we are looking at 1.5 degrees. We have our latest results with 0.25 degrees. But really, I think the more resources we can get towards these efforts, the best. I saw a recent paper for Taiwan specifically, which was even 10 kilometers. That's 0.1 degrees. So the resolution can be improved. It will need much more GPU resources to train those at higher resolutions. Actually, one of the experiments, it's in the paper, I don't have it here, is also you can take a coarse model and combine it with, these models are flexible enough that you can combine them with fine resolution data as a fine-tuning step. So that's also possible to make these models more useful for the resolutions that are of interest to the downstream application.
Thank you.
So the second challenge I wanted to touch on was about the geometry of the problem. So we have seen with, when we look at language, audio, visual data, these are actually just not as high, not very few modalities, right? So images is just red, green, blue. For videos, you might add a time dimension. Language and audio are just 1D sequences. On the other hand, atmospheric data actually has a very rich and complex geometrical structure. So naively, we all are used to looking at these flattened out globe maps where we see a longitude, latitude, and we have lots of variables for which we can have these kinds of maps. But there's also this aspect of time where we can look at these dozens of weather variables in space and as well as time, as well as also in terms of their pressure levels. So at different altitudes as well, we can look at these variables. So if you combine all of these different channels and in both time and in their pressure levels, we actually find that this becomes a very, very multimodal problem. So one of the things we have done is we have designed ways to actually improve the embedding of these weather kind data. And this is something which has been very useful. So naively, what one can think of this data is it looks similar to visual data. And since we're using transformer-based architectures, the conventional paradigm to dealing with such data is to flatten it out as a sequence of patches. So you can convert this into a sequence of patches, but because you have so many different channels, because of the number of variables, the number of pressure levels, the time steps, the sequence length can become huge. And that we know is one of the failure modes of transformers if you have like really, really long context lengths. So what we did is we designed a new tokenization scheme where we first embed each of these channels separately. But then very soon after, we figure out a way to then aggregate the different channels using a cross-attention operation. So this way, we do account for the variability along different channels in the early tokenization step. But in the future layers, when we actually have the transformer blocks, we are making sure that the inputs to those blocks happen to be one where the channel is not a bottleneck into the length of the sequence being attended over. And this is actually very important compared to the regular VIT architecture to get good performance. So here again, there's an ablation plot showing that if you just use the normal VIT approach of dealing with such data, your errors are much higher compared to using this weather embedding approach. So far, our results have not suggested any benefits with using more sophisticated approaches based on graph neural networks or 3D transformers. But I think that's a direction being pursued by other labs and is something which could also be useful in the future. The last part of this talk, I want to focus on how do we adapt these models to new tasks. So when we think about generalization in machine learning, our standards have actually increased over the years, which is really good news. Traditionally, it was just train and test being different in the sense of the instances being different. In modern machine learning, we are thinking of the task as well being different during training and testing. So you could be training on medium range weather forecasting in the order of 7 to 10 days, and then thinking about how these models will generalize if you want to make predictions for seasonal timescales. But really, if you want to think about sustainability and the role that weather and climate play in all of sustainability, we also have to think about how the modality can be different when we are going from the training of a model to its deployment for different kinds of use cases, like in agriculture. So this generally, I would think of this as a form of cross-modal generalization. And really what we're thinking is that you can pre-train your model on the weather forecasting objective like I described before, and you can scale it up in both data and model sizes. But then during fine-tuning, you might want to apply it to a different task. So for instance, in our case, we thought about going from weather to climate. So we were thinking about climate model emulation, because this is a really important task that atmospheric scientists care about. Because this really looks at how do the different greenhouse gases change our predictions for variables. And these variables are not the same as weather, but they are related. So when we look at precipitation and temperature in the future, we are looking at average statistics of pressure, precipitation, temperature, as opposed to point statistics that you would care about in a weather forecasting application. So that's the general difference, that both the inputs, these inputs are not something that you have exposed your model to during pre-training. The outputs are also aggregated, and they are at time scales much farther away than what was exposed during pre-training. So you want to think about how the same backbone can generalize to then these related tasks, but with involving different sets of inputs and outputs. Now, the challenge is often when you care about some of these new tasks, you may not have so much data and compute that you had for pre-training. So we have to really think of methods which are not prone to overfitting when we think about this cross-modal generalization. So one of the approaches we had designed a couple of years back, and this is again one of those examples of a technique which applies much beyond atmospheric foundation models, is to think about how language models can then be applied to arbitrary modalities. And here we really went into the details of the transform architecture and thought of all the learnable parameters, out of which the multi-head attention and feed-forward actually occupies 99.9% of the parameters. So if you have to really think about ways to do efficient fine-tuning that do not involve a lot of compute, then we have to think of how can we skip these kinds of parameters and use other parameters. Now, of course, there are other techniques based on LoRa and so on and forth, but back in 2022, our hypothesis was that for cross-modal generalization, we can look at the other set of parameters outside these two. So we had this work which showed that you can actually freeze these sets of parameters, so the attention and MLP layers, and fine-tune only the remaining set of parameters to achieve generalization much beyond language. So a language model could then be used to solve logic problems. It could be used for code prediction. It could be used for vision, proteins, and so many other different domains, only by fine-tuning 0.1% of the parameters in this whole network. So this is a good result because now, of course, the technology has improved much more. Language models are much bigger. There's a lot of investment being made to get good quality data. And all of these can also enable their use across other applications outside of language. So we adopted the same approach from our previous work to Climax, where we thought about how we can go from weather to climate. And here, again, we had different inputs and outputs, like I mentioned in the climate model emulation task. And here we're looking at the reduction in RMSE for these different variables that a climate scientist would care about, but not so much a weather scientist. And here we find that actually the same model can be fine-tuned to get good results. So compared to a random forest or a GP or a CNN, we find that our approach is generally comparable or better, doesn't overfit, even though these data sets are really small. And a frozen approach is not just equal or better, it's also much, much faster to converge. So there's benefits of doing this kind of parameter efficient fine-tuning for arbitrary domains. Now, in our paper, we actually have more results on downscaling, on regional forecasting, on forecasting and S2S time scales, where we use a similar recipe where the same base model is being used for different downstream tasks. But going beyond even weather and climate, now our approach has been used for wildfires and agriculture prediction. It's been used for predicting damages from natural disasters. And we ourselves are collaborating on our end with Amazon, which is the Institute for Preserving the Amazon, for predicting land use patterns over time, and also with the Argonne National Lab for predicting extreme weather events and their implications more broadly. So there is a wealth of applications that an atmospheric foundation model can enable, and this is just the beginning of what I feel the community can build upon. So this finishes the three main parts of my talk. I just want to take a couple of last minutes, just thinking of my broader perspectives on this discipline. So I really think of AI and its intersection with atmospheric science as a new form of engineering science. So engineering is important. It's a science in itself, how to take domain knowledge and combine it with machine learning to build new systems. And once we have these systems, they will enable us to do new science by understanding where these models outperform traditional models. But doing so requires high quality dev tools. So that's why we created this PyTorch library, built in our own experiences trying to understand this domain. So it contains lots of different data sets and benchmark, the different tasks I described, various kinds of models, both traditional and deep learning based, as well as clean evaluation to enable this kind of research more broadly. And it's all open source and available, so please feel free to check it out if this is of interest. With that, I'd just like to thank all my students, especially Tung and Jason, who led a lot of these efforts, as well as different sponsors for supporting our research. Thank you.
Thank you so much for a wonderful talk. We can start with some questions. I can start the first one. This is amazing, and also especially for the first part where you use transformer to predict this, like snapshots into the future, or maybe also the past. But I noticed these days more people model this in a more probabilistic way, like using the future models or flow models, where they can also turn this to a regression problem. Do you have any comments on those models?
Truly, I think, and these are actually complementary. So we are actually in the process of implementing diffusion architectures which use transformers. So even if you see the latest models like Sora and so on forth, these use the DIT architecture. So you can have a diffusion objective, but parameterize the networks using a transformers. And I think that's a very promising step ahead.
Any other questions?
I could ask one more. Is no one else? Can you hear me, or do I have to? Can I speak loud? Yeah. Obviously, you cannot hear.
Hi, thank you again for a very interesting work and very important work. Maybe one more question. If you think about the weather forecast models that people are using right now, it's not only pure data driven, it also incorporates a lot of physical insights and even some fundamental mechanism, based equations, etc. So I was wondering if you ever tried to incorporate any physics, or maybe you already did that into this foundational model, and do you see any possibility to do that? Because if you think about a way as an open world exploration or as a world simulator, we need the physics to govern the systems, right? Rather than being a pure data-driven system. And maybe more a naive question, right? We have this extreme heat last year. And I was curious, since your paper was published, have you ever made a prediction about extreme heat last year, or how was that data last year influence the future projections based on the foundational models you're developing?
Yes, I think both are great questions. To answer your first one, yes, I definitely think physics is quite important for these models. What we need to think about is what is the best way to inject physics. Traditionally, we are used to having a different kind of loss function, or we might make our architecture different in a certain way to respect the physics. For example, in applications in physical chemistry, for instance, that's normally the case. In our setting, you could do some of these different changes. So you could have a loss function which makes the predictions more physically consistent. The way we have adopted so far is to go into the data. So our data, when we look at simulation data, combining it with real data, a lot of that simulation data has come from physical models. So that we find is also actually a way in which you can include a wide range of physical laws into these models, but doing so without disturbing the optimization. So I think that's the approach we are taking. But as and when we get better loss functions or architectures which are not competing with traditionally the ones used in machine learning, those things could also be complementary. Your second question was about how are these models working, right? So there's a lot of news about these models, not just ours, but also by other labs like Google DeepMind and so on, for that they're doing better than physical models. What happens in the real world? So actually, ECMWF, which is the gold standard organization for doing these kinds of testing, they did do the test of these models for predicting hurricanes. And I think they did it for October 2023. So that was a month which these models had not seen during training. So it was a real world test, and they actually found them to do really well. So there is, of course, it was like a one-off experiment that they did. If you really want to deploy them, you have to do much more careful testing across a range of extreme weather events and at different locations in the globe. But the early signs look really promising.
Well, now is a good time to test because we've heard due to the warm water temperatures, it's going to be a very severe hurricane season.
Yeah. And in fact, actually, ECMWF, they have started releasing two kinds of forecasts now. So if you go to their website, they have a traditional forecast, and they have some AI forecasts which they have collaborated with, I think, Google to release their forecast. It's actually now, if one builds the proper tooling, we can actually test them on a lot of different extreme weather events for this year and going forward.
Right.
Well, maybe I was going to ask Fancy's question, so, but elaborating a bit on that, Aditya, there's also the difference between weather and climate. Can you talk a little bit about that?
Yes, and that's a great point where I think most of the research in the community has focused on weather, and part of that is because the goals are very clear. You have an input and output, and you want to get the best prediction for your future temperature and precipitation and whatnot. For climate, I think even the goals of the community and how machine learning can help are still in the process of being defined, just because we don't have any ground truth. So in climate, for instance, we have so many different modeling groups. Each of them have a different simulation of the physics into the future. So what's happening more of now, and some of our last few experiments I talked about, is emulating climate. So we can not do better than what these climate models are predicting because we don't have any ground truth. But perhaps machine learning can do these things much faster, which will enable us to imagine many more scenarios than what a climate modeling group can do without AI. So that's the big promise in terms of doing faster exploration of how the future could look like. But there are no guarantees of how correct that would be, just like any physical model gives no guarantee of how the climate could look like in the future. It's just a simulation of possibilities.
All right. Let's thank Aditya again for the
Well,
wonderful.
Yeah, thank